Okay, so with rational functions, we talked about last time that we can find domain and x and y intercepts. The other kind of things we can find are asymptotes, okay? So that would just be the restrictions on the graph and kind of where it goes and can't go, essentially, right? So, just as an example, if we have at 1 and then here at -2, we're saying that x equals -2, so this one right here is a vertical asymptote. That is how you spell it. It's a really weird word. And then that y equals 1 is a horizontal asymptote. Okay? So, how do we find these, right? If we just look at a rational function, what are they? So, to find vertical asymptotes, that's the easiest of them, we just set the denominator equal to 0. We're finding the restrictions on the domain. So, they are restrictions on the domain. So we're setting the denominator equal to 0 and solving for x, essentially. And that will give us our vertical asymptotes. Okay? So let's do some examples of that. If we're given f of x is equal to 3x minus 2 over x minus 4. And we're just wanting to find the vertical asymptotes. We're literally just saying set x minus 4 equal to 0 and solve, so that's x equals 4. So that means just graphing the asymptote would be at x equals 4, so just right here, if this is 4. Okay? And then there's more to it, obviously, with the graph, but that's just the vertical, and that's all we're looking at right now. Okay? And then if we were given g of x is equal to 3x minus 2 over x squared minus 3x minus 10, again, just set the denominator equal to 0. So x squared minus 3x minus 10 is equal to 0. Well, how do we solve that? Factor into what? -5 and +2. You get our -3. So that means x is equal to -2 and 5, right? So again, just graphing the asymptotes. -2 and +5. Okay? And then the graph is doing something around those asymptotes. So, what it is doing in kind of that area is it will get really close to the asymptote in either the positive infinity or the negative infinity direction. Okay? It will never reach that point because what we're saying here is x really can't equal these values, right? Because the domain of this function would be what? What would the domain be here for this one? Negative infinity to -2, yep. Union -2 to 5. Union
5 to infinity.
and then 5 to infinity. So we're literally saying that we can't plug -2 or 5 in to the function. So that's why we have those vertical asymptotes, right? So then, more or less, the graph is going to do something here, like it will maybe approach from this side, like that. I don't know, I just drew something on the graph, okay? So, it just gets really close to that value in either the positive infinity or negative infinity direction, okay? Got any questions on this so far? Okay, so we talked about how to find vertical asymptotes. Now, how do we find horizontal asymptotes, right? So what we're saying here is if we have f of x is equal to g of x over h of x, okay? So we're going to assign them a degree because it depends on the degrees. So the degree of g of x we'll call m, and the degree of h of x we'll call n, all right? So, first option is if m is bigger than n, meaning what? That the top degree is bigger, right? So the top is bigger, essentially is what we're saying. So, what happens here? What we're looking at is that if the top degree is bigger, then f of x will be a big number over a small number. We're being very scientific here, okay? So if we have something really big over something really small, well, that's going to give us a really big number. Or if we keep going towards infinity, it will give us infinity. Does that make sense? What I'm saying here? Yeah? Kind of? No? Think about it this way. If I have 2 divided by 1, that's 2. If I have 4 divided by 2, no, that's a bad example. If I have 4 divided by 1, it's 4. 4 divided by 1/2, well, it even flips and it turns into 8, right? So as our top gets bigger and bigger, our bottom gets smaller and smaller, okay? We're going to a really big number. The top wins, basically. That's the important thing here, is that the top wins, okay? So again, very scientific that it wins. So, when that happens, there is no horizontal asymptote, okay? So, no horizontal asymptote. So let's look at the other 2 options, because we said that m was bigger than n. So let's do if m is less than n, or in this case, that means the bottom degree is bigger. Okay? So this is the important pieces of each thing. Top bigger, no horizontal asymptote. Bottom bigger, well, what that looks like is we have f of x is equal to a small number in the end over a bigger number. If we have something really small being divided by something really big, well, think about it. The more times we divide something, the smaller it gets, right? So if we could actually get to infinity, we would get to 0, okay? Meaning that our horizontal asymptote is y equals 0. So, top bigger, no horizontal asymptote. Bottom bigger, y equals 0. Then, third option, if they're the same. Okay? So literally just they're the same degree. Not the same exact stuff, but the same degree. Okay? What that means then is, let's say we had like an example, just to look at it. If we have f of x equals 3x to the 5th plus 14x over 4x to the 5th plus 10. If we go towards putting in a really big number, infinity kind of thing, these are negligible. They don't really do much when we're talking about having to the 5th power, right? So it's kind of almost like we can kind of get rid of those. Okay? When we get really big, as x goes to infinity. So what happens then, just 1 second, is that the x to the 5ths end up kind of canceling out too, because we really are saying that we're going towards 3x to the 5th over 4x to the 5th, right? But, well, that's simplifiable, right? That's just 3/4. Okay? Because what we're saying is, as we get to plugging in a really big number, the non-highest degree terms don't do much for us. So we can kind of just toss them. Okay? Again, not scientifically stated at all, but that's the idea. So we only then have the highest degree terms, but we can simplify that to just the leading coefficients. So, in this example, the horizontal asymptote is y equals 3/4. Okay? So, it equals the leading coefficients of the top and the bottom. Alright? So, it's the leading coefs of top over bottom. Question now. Did I kind of answer it? Or did you forget?
So, what, like 5 to the 5th power is a big number.
Yeah.
So, what power makes it not so big that you don't cross out? None?
None. If it's the same,
You can just cross out.
we can always do this, right? It's the fact that the degree of the top is the same as the degree of the bottom. That's what's important. It could be linear on both top and bottom. It could have been just 3x plus 4 over 4x plus 10. It could have just been that, and it still would just be 3 over 4. It could be 3x to the 100th over 4x to the 100th with the 4 and the 10. It doesn't matter as long as they're the same degree. That's what's important. Does that answer your question? Okay. Any other questions? Okay, let's do some examples where we have to find all of the asymptotes. So, if we have, we're going to do multiples. So, f of x is equal to x minus 3 over x squared minus 6x plus 8. So, let's start off with the horizontal, the vertical, okay? So the vertical, how do we find that? Set the bottom equal to 0. So x squared minus 6x plus 8 equals 0. How does that factor? X minus 4, x minus 2. What would happen if it doesn't factor? There's no vertical asymptotes. So if this was a minus 8, no vertical, okay? So it's all dependent on factoring. Okay, then, so x equals 2 and 4. Those are our two vertical asymptotes, okay? So then what about horizontal? Which is bigger? The bottom degree is bigger because we have a squared. So bottom bigger means y equals 0. That's it. That's all you have to do. So the horizontal, because the bottom is bigger, you get y equals 0. So that means it kind of looks like y equals 0 is just the x-axis, so we kind of do a sideways lines to show that it's an asymptote on the x-axis, because you can't do a dashed line on top of a line. So that's how we do it. And then you have 2 and 4. So this is y equals 0, x equals 2, and x equals 4. Okay? Just realized I didn't turn this. There. Questions on that one? All right, so then next is g of x is equal to x squared minus 3x minus 4 over 2 minus x. So, start with the vertical. So 2 minus x equals 0, or x equals 2. Now the horizontal. So, degree, which is bigger?
Top.
Top. Because the 2 is bigger than the 1, right? So that means top is bigger. So, no asymptote of this direction. Right? Now, third example. Guess what type it'll be?
Same.
Wow, you read my mind. So if we have h of x is equal to 5x minus x squared over 3x squared minus 27. So let's start off with the vertical. That means 3x squared minus 27 equals 0. Then what?
3x squared equals 27, and divide that by 3.
Okay, 3x squared equals 27, and then divide by 3, so x squared equals 9. So then x equals
3. Plus
plus or minus 3. Don't forget, quadratic gives 2 answers, mostly. So, now let's do the horizontal. What degree is bigger?
The 1. Oh, they're the same.
They're the same. Don't get confused because they put them out of order. Doesn't matter. So that means It's y equals what?
Just the coefficients.
The coefficients, so -1 over 3. So I didn't do it on this one, but let's go ahead, we'll draw it. We have -3 and +3 and -1/3, right? So we haven't had any that have been like this yet, but the only thing that you have to check with this is if the vertical asymptote value, whatever that is, does it make the top equal 0? Okay, so what I mean by that is if we have f of x equals x squared minus 5x plus 4 over x minus 4. Yeah. So, if we go to find the vertical asymptote, we would set x minus 4 equal to 0 and get x equals 4. If we plug that into the top only, so if we do 4 squared minus 5 times 4 plus 4, we get 16 minus 20 plus 4, which is 0. That means it's not an asymptote, because what this really looks like, the top factors, right? So that would factor into what? X minus 4 and x minus 1 over x minus 4. Well, those x minus 4s cancel. Not truly, because 4 is still not part of the domain, okay? So the domain is still -infinity to 4 and then 4 to infinity, but we don't have a full asymptote there. What happens in cases like this is it's a hole in the graph. So the graph looks like x minus 1. So this is what it looks like, with a hole at whatever the point would be when x equals 4. So what I mean by that is we have the line x minus 1 that's here-ish. If this is -1, I can't write, -1. So if we plug 4 into this point, or into just this part, the x minus 1, we'd get 3, right? So if we do y equals x minus 1 and we plug 4 in, we get y equals 4 minus 1 or 3. So we go out to 4, 3, and instead of a full line, we have an open circle there. That's what that graph looks like. Okay? It's really weird, but all it is we're saying, because in the very original version of this function, we had x minus 4 in the bottom, we can't plug 4 in. But every other place for this function, it behaves just like x minus 1. That's what it looks like. We just can't plug in 4. Okay? So, the gist of all that is, when you go to find your vertical asymptote, plug it into the top to see if you get 0. If you do, it is not a vertical asymptote. Okay? Questions on that? So if you don't get 0, if you get like 7 or something, cool, it's an asymptote. Move on.
So only if it's a 0.
Only if it's a 0 at the top. because what we would get if we plug in here, right? If we do f of 4, we'd get 0 over 0. That's indeterminate. There's a whole thing of what that is. We won't get into it, but is it 1? Is it infinity? Is it nothing? It's a whole issue. Yeah.
So, do we have to do that in every problem?
You should.
We have to check?
Yes. If we go back and check our 3 examples, none of them make the top 0, right? First one we had 2 and 4. Only 3 would make the top 0. Second one we had 2. Well, 2 squared is 4, minus 6, minus 4, that's negative 6. So again, not 0. The last one is plus and minus 3. 3 would make that 15 minus 9, that's not. Negative 3 would make that negative 15 minus 9, that's also not 0. Okay? So we purposely did examples that don't have that happen, and then I just did an example that does make it happen.
So this is the check.
It's not going to happen that often. Okay?
This is the check. Like
This is the check. This is the bad check. Yeah. Okay? So, the main part of 4.6 is asymptotes. Okay? Vertical, pretty easy, just the bottom. Just make sure it doesn't make the top 0. Horizontal, top bigger, that's no good, so we don't have one. Bottom bigger, that's fine, just y equals 0. If they're the same, leading coefficients. I would literally just write that out somewhere, right? Literally just that part. It's a little cheat sheet for yourself until you get it down. But that's 4.6, that's it, okay? Now we'll go into 5.1. 5.1 is exponential functions, okay? So what I mean by an exponential function is f of x equals b to the x, where b is the base and x is the exponent, okay? So now we'll go into exponent rules. All right, we have quite a few of them, 7 to be exact. So exponent rules. First one is if we have b to the m times b to the n, what do we get? Anybody know? So we're multiplying same base.
Yeah.
We add the exponents, so m plus n. That's an n, not an h. It's the issue with using n's and h's. 2 is if we have b to the m all to the n, what do? We multiply, so that's b to the mn. So what I mean by that is we have 2 squared cubed. What that is, right, is 2 times 2, and then times 2 times 2, times 2 times 2, that's 2 to the 6th, which is 2 to the 2 times 3, right? So we're enumerating it, essentially. Does that make sense? Okay, then, third property, if we have b to the negative m, what does that do? We want a positive exponent. We flip it, we move it to the other part of the fraction. So if this was in the denominator, we move it up to the top. If it's in the numerator like it is, we move it to the bottom, exactly as it is. Just 1 over b to the m. Then, fourth property, if we have b to the n over b to the m, so we're dividing same base, what do we do with the exponents if we want to combine to the top? We subtract. So we have b to the n minus m. The other way we could do it, if we wanted to go to the bottom, would be 1 over b to the m minus n. Whichever one you move is the one you subtract.
Which way is better?
I'm sorry?
Which way is better?
It's dependent on the problem. So sometimes you want it in the denominator. Sometimes you want it in the numerator. It really just depends. Most of the time, we'll want it in the numerator. You just kind of have to have a feel for the problem. If you do it to the wrong one, well, it's just going to add another step. You just then have to move it next time. Not a big deal. Okay? Then, if we have, so the fifth rule is b to the 0. So anything to the 0 power is equal to 1. Sixth rule is if we have a times b, so two different things being multiplied to the m, that means we can just separate. As long as it's multiplication or division, that's the next rule, okay? If we have a plus b or a minus b, we can't do this. Okay, so that's a to the m times b to the m. Conversely, the seventh property is a over b all to the m is a to the m over b to the m. Okay? So, let's do some out. So, if we start off with 5 squared times 5 cubed, what do we get? You don't have to multiply it out, just 5 to the 5th, because we add. We have 2 squared to the 6th, we end up with 2 to the 12th. We have 1 over 5 to the 6th, and we want to write it with just powers of 5, so 5 to the what? -6. If we have 1 over 4, we want to rewrite this as a power of 2 in the numerator. So what that means, first step, 4 is 2 to the 2nd. Now we want to move it to the top. So this is 2 to the -2. Okay? That's how we would write that as a power of 2. Does that make sense? So that literally just means you want 2 as your base in the numerator. Okay? Then 3 to the 0 is equal to 1. 5 times 3 to the 0 is equal to 5. X squared times x cubed is x to the 5th. X squared to the -6th is x to the -12, or 1 over x to the 12th. So you have options. Just depends on what they ask for. If they ask for x to a power as a power of x, they want this one. If they want x with positive exponents, they want this one. Then if we have x over y cubed all squared, and we want to simplify, just simplify, you don't have to move anything around. That is x to the squared over y to the 6th. Yep. And then we have 1 over 5 to the 3x. So we want it as a power of 5. So 5 to the what? -3x. Then x to the 5th y. We want to simplify this. So, do coefficients together, and then do x's together, and then do y's together. Right? So, what would our coefficients be? 8. Just 8, because we just do the 2 and the 4. Now, x has what power? 7, because we add the 2 and the 5. Y is to what power? 4, because again, we add 3 and the invisible 1. Okay, so we just did a whole bunch of exponent rule problems, right? Any questions on any of those? Do y'all make sense? Okay. So, now, if we have this theorem, that if we have b to the u equals b to the v, that means that u equals v, okay? So, an example here, if we have 2 to the x equals 16, we want to make it fit this theorem. So basically we want to rewrite 16 as a power of 2. So 2 to the x equals 2 to the, what, 4? Because 2 to the 4, 2 times 2 times 2 times 2 is 16. So that means that x equals 4. Okay? Does that make sense? Just a kind of basic one to start us off. Okay, so then if we have five to the x minus 4 equals 1 over 125. Again, we want to use this rule. So, what is 125? How could we rewrite 125 as 5 to a power?
5 to the 5.
Not 5 to the 5th, 5 to the 3rd. And then, well, we can't match it yet because it's not the same. So we went 5 to the x minus 4 equals 5 to the negative 3. So now we have the same base, so that means the exponents must equal. So x equals 1. Right? How could we check this? Plug it in. Go back up right here. 5 to the negative 3. Well, isn't that exactly what we said 1 over 125 was? Yep. Okay. Are we good on that? Still so far? Let's see. Was there another one? No. Okay. So, now we're going to introduce the exponential function as a graph. So, what we want to do is graph f of x equals 2 to the x. So what we'll do is just write out some values. So let's plug in our normals, -2, -1, 0, 1, and 2. So if we plug -2 in, let's just kind of enumerate it out. We have 2 to the -2, which is 1 over 2 squared, which is 1/4. And then we have 2 to the -1, which is 1 over 2, and we're done, right? 2 to the 0 is 1, and then 2 to the 1 is 2. 2 squared is 4. So now we can graph this out. So we have that, and we have to go up to 4, So we have -2 is 1/4. So if that's a half, that's a fourth, so approximately there. Then at -1, we're at -1/2, so approximately there. At 0, we're at 1. At 1, we're at 2. And then 2, we're at 4. So we're essentially there. Then, what does this kind of look like? An asymptote, yes. So, this function has an asymptote along the x-axis, or at y = 0. So, it has a horizontal asymptote at y = 0. All exponential functions do. Okay? As long as they're not shifted, okay? Because then the asymptote's shifted. So if we added 1, then we would add 1. Does that make sense? It's just the whole thing gets moved up or moved down. If we move to the left or right, doesn't change it, right? Because you can't change something horizontally that is horizontal, right? Okay, so also, is this graph 1 to 1? How do we tell that again? A horizontal line. So, does it pass the horizontal line test? Yes. It looks like it kind of doesn't here, but it just gets really close to flat. It doesn't ever actually get flat, okay? So that means this function is also 1 to 1, which means it has an inverse. We will get to that in the next section, okay? Not today, kind of thing. But what is kind of going on here, right, is that we have this graph that is always what type of behavior? Not what I'm looking for.
Oh, like the positive?
Positive. We say it a different way. Increasing, right? So it's always increasing. Has an asymptote at y = 0. What would happen if we made it, I want to do it because I already have the nice graph up. If we made it g of x equals 1/2 to the x. What is that? Let's rewrite that. 1/2 is just 2 to the -1. When we have multiple layers of exponents, we can multiply them. So this is really just 2 to the -x. What does the negative on the x do? It's a reflection around what axis?
X.
The y-axis, right? So it's this way. So instead of going up, it will go, let me do a different color just so that I don't confuse that graph completely. It goes down instead. Okay, it just flipped around the y-axis. It's still the same graph, more or less, right? Same points and everything, for sure. Okay, does that make sense? This one is called an exponential growth. This is called an exponential decay. So this is now when we get into the science portion of the class, because exponential growth and decay are with populations, okay? So the formula that we'll see with these graphs is P of t equals P0 e to the kt. Okay? That is an exponential growth or decay function. You will deal with those a lot in methods, especially if you take life science. Okay? Any questions on exponential functions? No? We're good? Okay, then do me a favor.